Hey everybody, Mr. Ellinger. Sorry about the weird lighting back there, and we're going to go over the practice test now. So here we go. Okay, the figure above shows a graph of the function f, which the following statements are true. Okay, so as you approach 2 from the left, that's exactly the same as the y value you get at 2. That would be true. As you approach 6 from the left on the function, that's the same thing as if you approach 6 from the right on that function. That would be true. The limit as x approaches 6 of f of x, which would be -1, because you're getting closer and closer to -1 on both sides, is equal to the y value actually at 6. No, I don't think so. Correct answer looks like C. Next one. Whoa! Okay. The graph is shown above. Which of the following tables could be? So what I'm looking for is I'm looking for something where when x equals 1, the y is equal to 7. So see ya and see ya, because at x equals 1, the y is definitely 7. Whoop, there we go. Y is 7. And then I need the limit as x approaches 1 to be 4. So as x approaches 1, I need the y values to look like they're getting closer and closer to 4, and that would be this one. It is known that the limit of sine 2x over 2x is equal to 1. That's true. What is the limit of, as x approaches 0, of cosine 5x over 8x cotangent 2x? Whoa, okay, this is going to take a little bit here. All right, so we want to know the limit as x approaches 0 of cosine 5x. And then we've also got an 8x. I'll put that just down here. And then we've got a cotangent in the bottom. So cotangent in the bottom would be a tangent in the top. And tangent is sine over cosine. So that'd be sine 2x over cosine 2x. Okay, this won't be so bad. All right, as x approaches 0, yeah. Just kind of doing a quick double check. Looks good. All right, now we know that as x approaches 0, sine 2x over 2x is equal to 1. So here's what I'm going to do. I'm going to go limit as x approaches 0 of sine 2x over 2x. And I kind of take this 8x and I'm just going to pull off 2x of it, and that would leave me a 1/4 left over. And then I still have these cosine of 5x. 5x over cosine of 2x. All right. Well, we know that the limit of this is 1. So now I'm doing what I call bite-sized chunks. I'm going to look at each part, and as long as each limit exists and it's just a number, then I can just work out each one individually and then combine them all together. So that one is 1. This one is 1/4, because as x approaches 0, this is infinitely close to 1/4. It is 1/4. And this one, I can plug zeros in now, because if I plug in 0 in there and 0 in there, I get cosine 0 over cosine 0, 0, which is 1 over 1, which is 1. And so the answer is, not scrolling, sorry, trying to scroll, there we go. The answer is 1/4. Yay! Next one. Let g and h be these functions. Cool. If f, okay, f is between the two of them. This is a squeeze function one, I can tell. We got a lower function, we got an upper function, and we got a function that's always in the middle. The question is, and that's true between -1 and 2, which is the only place I care about, because I want to know what is the limit of f of x as x approaches 1. Well, this one, as x approaches 1, I can just plug in that g, the limit, I'll be clear, the limit of g of x as x approaches 1, I can put in the 1 there, and so that's sine of pi over 2, which is 1, plus 4, which is 5. The limit of this one as x approaches 1, the limit of h of x, as x approaches 1, I can plug in 1 over, okay, so 3/4 plus 9/2, oh man, so that's 2/4, so is 1/2 plus 9/2, which is also 5. Yay! So the bottom one's approaching 5, the top one's approaching 5, that means the middle one's approaching 5. Next one, 5. The limit is what? Plug in 2, I get 4, 6, I get 0 over 0, do some work. So it's having trouble with OneNote there. So it's x plus 3 times x minus 2 over x plus 2, x minus 2, limit as x approaches 2. On a multiple choice question, you don't have to show all this work, but I'm just trying to be clear. And so these would cancel out. And as x approaches 2, that gets close to 5, that gets close to 4. And the answer is 5/4. Next one. As x approaches -7, what's the limit of this thing? Okay, so let's think if x is... So this is getting closer and closer to 0, and this is getting closer and closer to 0. But as you plug in numbers that are close to -7, like... Okay, let's give an example here to make it clear. And I'm not going to use a calculator on this. So like if I plug in something like -6.9, so call this f. So f of 6.9, -6.9 would be 0.1 over, right? Yeah, and the bottom would be -6.9. Yeah, it would also be 0.1, so you get 1. Right? Now when I plug in f of -7.1, so I'm going a little bit to the other side to say, on the other side, what is this really close to? And then it would be -0.1 over still 0.1, which is -1. These numbers are going to be the same, except on one side, they're going to be opposites, and so you get -1, and on the other side, they're going to be the same number, and so you get +1. And so you have this graph like this, and this was one that you should have learned last year in Honors Pre-Cal. It would be at -7, and it would be a hole here. Yep, just double checking, make sure I had it on the right side. And there, this would be at 1, this would be at -1. The limit does not exist. Next one, 6 minutes. Okay, we're doing good. Let f be that. Which of the function? Okay. Oh, what kind of discontinuities does it have? Okay, so it's x squared times x squared minus 4. Which is x squared times x minus 2 times x plus 2. Cool. And the bottom, I can pull an x out. So the bottom is x times x minus 4. Check your factoring. You need to be able to factor top and bottom pretty confidently. All right, so it's got 2 places that are discontinuous, or it could be that, I've got issues, 0 and +4. And so I only want... Yep, all of them have 2 discontinuities. Okay, so that doesn't help me. I was seeing like if one of them had 3 discontinuities, then I could cancel that one out. Not an option. So now you simplify it. Say, can I simplify it at all? Like right now in the beginning, you say x can't be 0, and it can't be 0. But what would happen if x was a number close to 0? Well, the thing is, if it was close to 0, it would cancel out with the x that's in the numerator, and it's not there anymore. So at x equals 0, it's got issues right at 0, but anywhere close to there, and it's not going to do strange things. And so therefore, that's what's called a removable discontinuity. Meaning that it's a discontinuity that you could fix by just defining the function. It's just got like this with a little hole that just has one value. The problem is very small. It's just this one x value. That's the issue. But x equals 4, that's got issues. If you plug in a number really close to 4, like 4.001, then the top is going to be 4 times 2 times 6 with some decimal points and stuff. It's going to be some number. But the bottom is going to be 0.01 because it'll be 4.01 minus 4. So you've got a number divided by 0.01, which is, you do it on the right side, I'm putting a number a little bit bigger than 4, which would be infinitely huge. And if you plugged in 3.9999, you have the same issue, except if you plug it in, you'll check it out, you'll get a negative. This is an asymptotic discontinuity. And so that's an asymptote there. Just need the right option. Discontinuity, vertical asymptote, no. It's got a removable one at 0, I agree. And a jump discontinuity, no, it's not a jump. It's not one of these things like we saw with that function just a moment ago. It's a vertical asymptote. Next one, we need to be continuous. So we need at x equals 3, we need these things to give us the same value. We've got one coming in at 3 and the other one coming in on the other side of 3, and we need to know they need to touch at the same place. This is a parabola. That's going to be continuous everywhere else. This is going to be a line, same thing, but what's going to happen right there? We need them to match up. So let's see. The top one at x equals 3, x equals 3. The top one gives you a value of 11, and x equals 3. The bottom one gives you 18 plus k. So we need, whoop, that's an 11 right there. So we need k to be negative 7. Cool. Which of the following functions are continuous? Woo! How many more do I have? Just do a quick preview. Okay, we'll see if we make it. I know that there's some long ones here. All right, let's do it. Which of the following functions are continuous on the interval 0 to 5? Okay, we need problems on somewhere between 0 and 5. Well, this one is not going to work because if x equals 3, it's undefined in the because of the denominator. And then the bottom one, that's defined everywhere, so yes. And the next one, x has to be a number bigger than 3 because you can't natural log 0, so x can't be 3. You can't natural log a negative, so x can't be less than 3. So therefore, because we need to work for everything from 0 to 5, that one's out. It's just number 2. Next one. Okay, so let's just go through. Okay, this is going to take a little bit. We need, as x approaches 1 from the left, we need the limit to be positive infinity. Whoa. Okay, that's not too big. We'll just do that. That's not too bad. All right, so this one is out because as x approaches 1 from the left, we're getting negative infinity. And so this one violates that one. You're good. You're going to infinity. You're going to infinity. You're not going to infinity. You're going to negative infinity. You're out. Okay. All right. What's the limit? I'm just looking at the difference between these two. One is getting closer and closer to 2 as x goes to infinity, and the other one is getting closer and closer to negative 2 as x goes to infinity. Which one's right? It needs to have a limit of 2. It's this one. Next one. Woohoo! Got by that. For which of the following does the limit equal 0? So we need the numerator be much smaller than the denominator because that's how that works. And so, like the first one, you've got as x goes to infinity. So you got infinity to the 99th. Whoa, that's big. And then natural log infinity, it's infinity, but it's not that infinite-ish. And so therefore, so this one is smaller over larger and significantly larger. And so this one, yes, it's true. Next one, e to the x over natural log, that's going to have a huge numerator, and big over small is going to be big. It's not going to be 0. That one's out. And the next one, x to the 99th, that's going to be big, and e to the x, oh, that's going to be big too. And this is that whole thing about polynomials are less than exponentials, which are less than factorials. That denominator, as long as you plug in a big enough x value, is going to be infinitely bigger than the numerator. That's the way exponentials work. They're steeper than polynomials. And so this one too. And so it's 1 and 3. Got it? Number 12, intermediate value theorem. Oh, last problem. And make it. Okay. Let f be a continuous function on that interval. Okay, so it goes from negative 3. It goes from negative 3 to 6. Great scale, Mr. Roger. Thank you. F of negative 3 is negative 1. So we're here at negative 3, negative 1. And f of 6 equals 3. And so we're up here, and it's continuous. So that means that it has to be a connected line to get up there. And so every single y value gets touched somewhere between negative 3 and 6. Which one is that? F of 0, 0? No, it's not, or it doesn't have to be. F prime of c, what the heck is that? Chapter 2. X has to be between negative 1 and 3. For all x. Now, my drawing looks that way, but it didn't have to be. It could have gone like that also. And so that one's not true. F of c equals 1 for at least one c. So f of c equals 1 for at least one c between negative 3 and 6. Yes, that's true. The second one is wrong because the x's don't go from negative 1 to 3. They go from negative 3 to 6. So the y value is 1 for at least one value, and it's an x value between negative 3 and 6. That's it. Minute left. Made it. Hope this helps. Please let me know if you have any other questions. This covers a lot of the basics from chapter 1. I won't say it's absolutely everything, but this will give you a good idea of if you understand what you're doing with limits. Okay, take care, and we'll see you on next Monday, a week from Monday. And remember, if you have any questions, please feel free to send me an email. I'd be happy to help out. Okay, bye.